Today we are going to recreate a classic simulation that was developed way back in 1997, and we're going to change it so that it matches a demonstration of a phantom traffic jam. And there's a video of that demonstration in the links down below. You can have a look. And along the way we are going to see some emergent phenomenon, which is super cool, and we are going to get to do some desktop social science from this desk. So let's get started. We're using NetLogo. Now I've got the NetLogo environment here, and this black square is where our simulation is going to happen. And what we're going to do is we're going to create agents, and we're going to tell the agents what to do. They're going to be little car agents that will drive around and hopefully get themselves into a phantom traffic jam so that we can study what's going on. And the settings for the environment can be changed up here. And you can have a look at the ones that I have created there if you want to have a go later on. And the only thing I've done so far is create a setup button. Now if we go to the code pane, we can write in the computer code that gets executed every time somebody presses the setup button. It goes between to setup and end. And so far all I've done is I've put the command clear all. Now clear all is really important because it clears the memory, and it means that there won't be stuff hanging around from the last time NetLogo was used on this computer. So it's always really important to execute clear all. Now the first thing I'm going to do is draw my racetrack, and it is only a drawing. It won't have any impact on the behavior of the agents. And to do that, I'm going to create an agent. I'm going to set the agent to be a certain size and shape, and I'm going to have them jump up and down in the environment to colour it in. That's essentially what's going to happen. Now in NetLogo, agents are called turtles. So I create a turtle, and I'm going to create one turtle, and then in square brackets I can specify the behaviour. Now my racetrack, my track is going to be circular, just like the demonstration in the video. So I want to set shape to be circular. Oops. Set shape circle. And what I'm going to do is I'm going to create a big white circle on top of the black environment, and then I'm going to create a slightly smaller black circle to go on top of the white circle to leave me with this circular track. And I experimented earlier, and the radius that I want to use for my circle is 44. Set color to be white, color being American spelling, and to have the turtle jump up and down is stamp. Let's run that and see what it looks like. So I press setup and I get a white circle, but we're not done with that turtle just yet, because then we want to change it, the size, to be a bit smaller. And again, I experimented, and 36 is I think what I want. This time I want it to be black. And then I need it to stamp again. And there is my track. Now I've still got a turtle in that environment hanging around that might mess things up, so I need to get rid of it. Now the command to get rid of a turtle is to tell it to die. Per turtle, sorry about that, but I did not write NetLogo, but that's the command anyway, to clear a turtle. We now have our track. The next thing we need are the cars to drive round our track. Now what I'm going to do is I'm going to put a slider on the interface, and I'm going to call it cars, and this will be the number of cars that appear on my racetrack. On my track, it's not a racetrack, it's just a road. Now NetLogo doesn't have a snap to grid, which is why these things never line up neatly for me. Actually, that's not too bad. So I'm going to create cars number of turtles. So in the setup button, I'm now going to say create turtles, and the number of turtles I want is cars. Now, what do I want my turtles to do? Well, first of all, I want to be able to see them. So I'm going to set size to be 4, otherwise they'd be quite small. I want my turtles are going to start in the center of the black circle here. And at the start, they will be given a random direction. It's called their heading. So a random heading, which might be straight up, it might be over to the left or to the right, it might be down, it could be anywhere around 360 degrees. And what I will have them do is just on the random heading that they start with, I'm going to have them move forward the radius of my circle. So I'm going to have them move forward 40 units, which of course is my first mistake. It shouldn't be 40, the radius is going to be 20. So let's see what that looks like. Okay, now these turtles have a heading that is pointed to by the tip of those arrows. And that gives a clue as to what we're going to do next. So we want them to walk out onto the track, onto the road, and I'm going to have them go clockwise. So I want them to turn 90 degrees to their right. And to do that, I set heading to be a new heading to be the old heading plus 90 degrees. And there they are. And I can do more of them and I can do less of them with my slider. Okay, what's next? What's next is I'm going to add a button to start them on their drive. Now you could call this button anything. You could call it start, you could call it drive, you could call it whatever you want. Usually people call it go. And what is going to happen when someone clicks this button, the program that has been written for the commands that have been written for go will be executed once. And that is what happens in one time period in our simulation. So they will drive a little bit, in other words. And maybe if we consider each time period to be 1 second, they would drive for 1 second. We don't want that. We want them to keep driving over and over and over. We want them to go forever, so we click forever. And again, we need to do some adjusting to make it look good. And it's red at the minute, and the reason it's red is because we haven't added any code. It won't be red anymore. And the code that happens gets executed in here. Now, what is our code going to be? Well, to get these things to drive around, what we can't do in NetLogo is have the turtles move in a curve. So what we're going to do is we're going to split our road up into chunks, and we're going to have the cars drive straight and then turn, straight and then turn, straight and then turn the whole way around. Now there's 360 degrees in our circle, so we could have them do this 360 times. Oops. So we want them to go forward. Now, in order to get the turtles to do anything, we have to ask them to do it. So we say ask turtles and then open a set of square brackets. And then everything in the square brackets is what these turtles, not turtle, will do. So we want them to go forward. Now, we want them to go forward around the circumference of this circle. And the circumference of the circle is pi d. And NetLogo has got pi built into it. So we don't have to make up a value for pi. We don't have to input a value for pi. We can just use pi. And it's pi times d, which is 40. Now, what value does NetLogo use for pi? That will have to be the subject of another video, and we will talk about that because maybe we'll talk about it on International Pi Day. Because the choice of pi is relevant for certain applications, so it might be interesting to talk about that. And we want that to happen 360 times. So that is our circumference divided up into 360. Now, each of these cars will be travelling at a certain speed, and they will all have their own speed. So what we're going to do is we're going to have them jump forward a certain distance, and that distance is their speed. So we need to give turtles a speed, and to do that we need to start by giving them a speed variable. So up here at the top we will give our turtles a variable called speed. So each car, each turtle will have a speed variable. And then down here in the setup we need to specify what that speed is going to be. So we get the turtles to specify, to assign themselves a speed, and the speed will be greater than 0 plus a bit that could potentially get them up to a maximum speed of 1. So we will use a random float, which is a random variable between 0 and the number we are about to specify, which is 0.9. So the speed for each of the cars will be between 0.1 and 1, with 1 being defined as the maximum speed that a car can go in our environment. Now, once they travel a straight line, they need to turn so that the heading is still 90 degrees to the center of our circle. And for this we need to dig out, we need to bother those two old angels. If you remember trigonometry from school, two old angels skipped over heaven carrying a harp. With tan of an angle equals the opposite over adjacent, two old angels. Skipped over heaven, that's the sine of an angle equals the opposite over the hypotenuse. Carrying a harp, you can work out for yourselves, or you can just remember it. Alternatively, we could just go to the models library in NetLogo and search for a model that has its turtles move in a circle, which is exactly what I did. However, if you want to know how to do the calculation properly, I will show you right now. And here it is. So you can freeze frame the video and have a look, but that's the center of my circle. That's the radius. This is the straight bit that the turtles have moved across. That's the 360th of the way around a circle. You can work out the value for this angle, and then down here, plug that in. I worked it out with a speed of 0.5 to be 89.5. That's the amount that the turtle has to turn, so you need to work out θ1. And if I just wait for the things to clear at the bottom of the screen, these things, I worked it out to be 0.5, which is the speed. So we want to rotate around by the speed. So when our agents go forward, they then set their heading to be heading plus their own speed. And that's it. And if we run it now, they should... Oh, have I not? Got too many brackets in. Set them up and go, and they spin round. And they don't do anything else at the minute. So what do we want to have them do? Well, what we want to have them do is approach a car at their speed, and as soon as they catch up to that car, they slow down a bit. So if there's a car ahead, they slow down a bit. If there's not a car ahead, they accelerate up to their speed. And the code to do that, I'm just going to copy paste it in, and then we'll talk about it. And I'm going to do that before I have them move. Because what I want to do is I want them to check that there's a car in front before they start, so that it avoids any crashes right at the very beginning. So let's have a look at this. Let car ahead. So what that does is that gives each turtle a new variable that's only temporary called car ahead. And that car ahead is going to choose one of the turtles that might be in front. So let car ahead be one of the other turtles, so in other words it doesn't include the turtle itself that you're asking, one of other turtles in cone. In other words, we're creating a vision for the turtle, and you can look up the syntax for that if you want, but basically we're going one jump ahead and the angle that we're looking is 60 degrees. And there might not be a car ahead, in which case the car ahead variable will contain this special value nobody, in other words a null, there's nobody ahead. Then we start an if statement, if else. So if the car does not equal nobody, so if there is somebody ahead, then decelerate. So set your speed to be the speed of the car ahead minus this value 0.026. Where did that come from? That came from the original implementation of this simulation. And so we match the speed of the car ahead and slow down a little bit. On the other hand, so else, if there's not a car ahead, then we set our speed to be a little bit faster. So that's our acceleration, and again that value comes from the original simulation. If at any point our speed drops to 0, then we keep it at 0, so we don't go less than 0. So that's what that line there does. If speed is less than 0, set speed to be 0. And we don't go faster than our maximum speed. So if the speed ever gets faster than our maximum speed, then we set the speed to be our maximum speed. Now, at the end of all that, we have to update our environment, and we do that with the display command. And that should keep things looking smooth. And I think that's it. I think we're there. I think we've done it. Let's run it and see. Oh, it's too fast. You'll notice that eventually the cars go wonky. That's okay. We just want to see what happens early on. Eventually they'll wobble and go out of alignment because of limited precision on this computer, essentially. Go a little bit faster than that. Okay, so there, you can see the cars here stopped. So despite the fact that there was no obstructions, there were no roadworks, there were no traffic problems up ahead, there was no crash, despite all of that, our cars got themselves into a traffic jam, and that is a phantom traffic jam caused for no reason, and that is our emergent phenomena, because in here in the code we did not program a phantom traffic jam. That just happened from this behavior. Now, not only that, but the code that we have created here is an explanation of a phantom traffic jam. In other words, it's a theory of traffic jams. So if people follow these simple rules, the behavior leads to traffic jams, it leads to traffic problems. We don't need any additional explanation for why traffic jams happen, and we've just created this explanation. And that is super cool, because the original implementation of this model, the people who wrote it, including Yuri Walensky, who wrote NetLogo or designed NetLogo, the program that we're using here, he wrote these rules and he thought that he would have to create an obstruction. He thought he would have to create a crash to generate a traffic jam. And it was amazing. He realized that he didn't have to, that these rules alone produce a traffic jam. Now, we also said, in addition to emergent phenomena, we said we would be doing some social science on the desktop and on this tabletop, not desktop. What we can do is we can run this model with the current settings and write down some data that we observe, and then we can make one change to our environment. For instance, we might lower the number of cars a little bit and run it again and write down some data, and we would compare what happens with 10 cars with what happens with 8 cars. And that's science. That is the scientific method right there. So science means, and we've said this many times on this channel, science is comparing 2 or more situations under controlled conditions. The conditions are controlled because they're identical with just one change. You can't change 2 things, otherwise you'll mess the whole thing up. You just make one change at a time and see what happens. Write down what happens. Or it might be that we put certain speed limits at certain points around our circle and see what difference that makes. Or we could reshape our road to be the shape of a motorway and up the number of cars and study what happens on a real motorway and compare different interventions that you might make to try and reduce traffic jams to see if any of them work. And there it is. That is social science performed in an agent-based model using NetLogo, and try it yourself, and I'll see you in the next video. If you like these, click subscribe down here somewhere. Bye bye.